Good afternoon. This is Mark Skidmore. I'm the director of the North Central Regional Center for Rural Development. Today we have, today's webinar is Addressing Mine-Scarred Lands in the Upper Mississippi River Mining Industry. Our presenters are Jeff Simmering and Kyle Pepp. Jeff is an outreach specialist at the Department of Soil Sciences at the University of Wisconsin-Madison. Kyle is a master's student in water and resource management, also at the University of Wisconsin. For those who are participating, if you have any questions, I just want to remind you of the chat function. You can just type in your questions or comments there, and Jeff and Kyle will either answer them along the way or at the end. So Jeff and Kyle, thanks again for being here and presenting your work. I really appreciate you being on for the webinar.
Thanks.
Thank you.
So you guys can go ahead and start when you're ready.
Okay, I'm still seeing the webinar title slide, or I guess I put forward? No?
Yeah, you just click. You should be able to click forward.
Up there it goes. Okay. Thanks for joining us today. Yeah, as Mark said, we're going to talk about mine-scarred land in the Upper Mississippi River Mining District. And this district is predominantly in southwestern Wisconsin. The ore is also mined out of northwestern Illinois and a tiny bit of eastern Iowa. Most of the mining here occurred between 1820 and about 1950. This is the part of the state that's the Driftless region, so it was not glaciated, so it's still fairly hilly, even if the peaks are not particularly high. Out of this region, there's an estimated 814,000 tons of lead were mined and 1 million tons of zinc. Now, we're not concerned about that because that's been spread all over the world and all over the country. What we're more concerned with is the estimated 40 million tons of ore that was extracted to produce that metal. That didn't leave the region. It's also high in lead and high in zinc, just not as high as the ore that was after where the metal was extracted from. So here's a picture of the Cleveland mine in Hazel Green, Wisconsin. As you can see, there are a lot of ore piles sitting around. So, and even after this mine facility has been disassembled and the structure's gone, those rock piles are still sitting there. Where that has all gone, that's a good question. So a lot of it probably ended up as roadbed or foundation material, anywhere where you need crushed rock. Because it's easier just to go to these piles still sitting there, crush them up a little more and take them off and use them that way. So also, here's another picture, Blockhouse Mine in Platteville, Wisconsin. As you can tell, agriculture has coexisted closely with the mining industry since, well, the 1820s. You've even got the farmer sitting there in the corner, sitting on the tailings while watching his cows graze. Also, unfortunately, the mines are in close proximity to human habitation. You can see the houses there in the background. This is also in Platteville, Wisconsin. Platteville's done some looking around on their own, and they're between 50 and 60 mines, test pits, or other exploratory shafts within the boundaries of the city. So they're still dealing with this issue. And got to keep in mind, this is lead that was being mined in a lot of these. So the likelihood of adverse effects to human health, environmental health are pretty high. So nowadays, this is what some of these sites look like. So it's not the big piles of rock, it's not the old derelict mining equipment. Up at the top end of this photo, you're seeing kind of this area where not much is growing very well. That's kind of what these sites appear like now. Extension agents get calls, not uncommon. There's a farmer saying, wow, I got this dead spot in the middle of my field or the edge of my field, just nothing will grow there. What's going on? This particular picture was taken in the spring, so it's all nice and green. By the middle of summer, that whole upper part is kind of yellow and looks bad. So when the farmer gets out there in his field, this is what he sees. Oh, man, this corn looks awful. How do I get more to grow? Because it pretty much just stops at about that height if it comes up at all. So the zinc toxicity and zinc deficiency in corn actually looks pretty similar. So sometimes crop advisors will, that's what they're diagnosing, will be zinc deficiency. So they send the soil off for soil tests. Look at it, comes back screaming high in zinc. But keep in mind, those soil tests, they don't look at lead. So that's kind of being forgotten in this scenario. Farmer just wants to grow more corn. Then there are the human health and ecological impacts. The picture on the left is downslope from the top edge of that aerial photo I showed earlier. So you get a big rain event, the water goes right towards that new housing that's going in, and there are additional housing going in just to the right of that house as well. Heavy rains also carry around a lot of particulate matter as well. So you kind of got a plume of lead and zinc-contaminated sediment heading towards these houses, which is really not a good thing. The picture on the right is another site nearby, and upslope of this little ephemeral, actually it's a year-round kind of small wetland and stream, are mine contaminated. Now the farmer here manages to grow something, so he keeps farming it. But this year-round water source is actually contaminated with lead and zinc in the sediments. So how does human health, how is it affected by lead? Well, we've heard a lot about that from Flint, Michigan, and East Chicago, Indiana. So we know in kids that it is very problematic. It's a neurotoxin, and it can lead to lower IQ and behavior problems. Most importantly with kids is because it affects them during the time that they're developing, those impacts are going to be lifelong. So it's really important to deal with this lead issue, any lead issue, early on. Adults can be lead poisoned, but the treatment there typically is that you eliminate the source of the contamination, the poisoning, and over several months the body will naturally excrete most of that lead and the effects will go away as well. So currently out in this area, these lands are kind of ignored. They're just low productivity land that either wasn't used or was covered in weeds. But as crop commodity prices have gone up, a lot of this land is being pushed into production. So now it's being farmed. It's easier to farm when you have great big farm equipment too, because these aren't large areas of land. So it's easier just to make a couple passes with your equipment rather than trying to drive around it. A lot of times this stuff is hauled away. In that aerial photo I showed you, at the top of it there, the first year we were there was a pile of rubble and some ore rocks sitting up there. Second year we came back, it was gone. Asked the farmer, hey, where'd this go? And he said, oh, I had it hauled away. It's like, well, where's away? I don't know. It's just away. So that's all lead and zinc contaminated, and now it's been moved from the site where it was to a new location. Now you've got another contamination spot. So what's happening is this stuff is being spread in a thinner layer over the whole region. Really what we like to have happen? Let's identify where these sites are. A lot of times it's been forgotten. People know that there's the mining history out there. It's not terribly uncommon to have sinkholes open up or houses fall in, mine shafts as they collapse. But the hazards have kind of been forgotten. It'd be great to control site access to these areas, or at least identify where they are, sign them. We'd like to eliminate off-site movement, not only from people hauling stuff, but also runoff. And remediation plans would be great to be developed. Few regulatory concerns. In Wisconsin, there is no innocent landowner provision under state spills law. If you have a piece of property and there's contamination anywhere on it, it's your problem. And if the state finds out about it, it gets listed on a contaminated lands registry, which does not do much for your property value. Farm succession plans in this area are beginning to require environmental reviews because in the past, sometimes farmers were not very good about disposing of chemicals like they should have. So in some cases, there's a strong incentive not to test for these contaminants. So we're trying to figure out how we can help. We got a couple initiatives underway. First is integrating mine mapping resources into current GIS-based mapping systems, and then working with local planning departments. Second, is a little more research, is investigating soil amendments to immobilize the lead and detoxify the zinc, and then exploring some low engineering options, alternative land use options. One is a pollinator island that we're seeing might work. And now I'm going to turn this over to Kyle, and he is going to talk about his mapping.
All right, so my name is Kyle, and I've been doing some of the GIS mapping and digitizing the historic data sources for these mines. Um, right now, there's kind of two major sources. There is the USGS professional paper written by Heil and others from 1959 that kind of details the geology of the area. And then the main one that I'm focusing on digitizing is the Wisconsin Geologic and Natural History Survey's Mineral Development Atlas. Basically in 1945, several federal and state agencies began compiling permitting information from the mining companies to begin to kind of map out and see where all these mines actually were and where most of the damage took place. It was finished in 1976, and basically the output of it is that there are square mile PLSS section maps that show some of the mine activity that took place there. And then on top of this, I also have current imagery and also some LiDAR hillshade data that you can really kind of identify some of the landscape changes that the mines left behind. To give you a better perspective of the area, the light blue coloring is kind of the size of it. And so basically, a little bit of a history of the mining process. Initially, it was just kind of lead surface mining. It was scattered all over the place. There wasn't really any consistent operations going on, and it was for Civil War munitions. The problem here is kind of surface lead contamination. In the picture right here, you can kind of see with the LiDAR hillshade these sort of crater-looking impacts, and this is kind of a lead digging site. And it's interesting to see that this 2015 LiDAR image is showing impacts from the 200 years ago that still exist on the landscape. And you can kind of see these farmer plow marks that kind of go over the top of some of these areas. The next major mining operation was underground zinc mining. And so basically at every one of these mine sites, the ore would get gravity concentrated at the top of the mine site, right immediately above it, and they just kind of toss the tailings near the mine site. And then after this, they would go on to roasting and magnetic refining on railways or in other segregated areas, but it still basically guarantees that there's a large tailings pile above or near above every mine site. And then as we move on into the after the in the 30s, we have new mining technology, and there's still a gravity concentration at every mining site, so there's still tailings again at every mine site, but now there's also these kind of acid slurry ponds that was used in the chemical refining process, and this kind of shows up on the map there. So the mapping process, basically, I start out. This is a picture of what the atlas data looks like, and then below it I have kind of a transparent hillshade layer. And so I go through and map out the boreholes, which are these little circles everywhere. Underground mines, which are these kind of big, long things. There's also unsurveyed mines, open pit mines, mine shafts, abandoned railroads. And the abandoned railroads, you can also see the tracks in the LiDAR hillshade as well, so you can kind of make sure and see how accurate the actual imagery they provided was. And then there's also these lead digging sites, which is this, and acid plants, and also the missing data areas. So overall, it kind of looks like this. Add the underground mine, add the boreholes, and then the lead digging site, and then after this you can start overlaying it with other things. So, and then after you do all that, then you can create a nice map, and right here is this is kind of a large area, about 30 or 40 square miles, and you can kind of see how densely these mines are in the landscape. Luckily, most of this is kind of a rural area, with the exception of this city right here. But This is one of the more densely populated areas, but it's still pretty extravagant in this area. Here's kind of a closer look at it. The purple are the big underground mines, and the turquoise are the lead digging sites. So in terms of planning, we can add other data to this now GIS-based map. Most importantly is probably city parcels, and you can kind of see right here these red outlines are city-owned parcels, and there's kind of some danger to know that, well, here's all these mine shafts, here's all this underground mining, and the city kind of may or may not know about this, and they have all these kind of subdivisions that are ready to be developed, knowing that there's kind of going to be runoff coming down here, or there has been for the last 100 years. In addition, we also add the impaired waters layers to these, and if you look in the attributes for them, you can see that they're all zinc and lead contaminated water, among other things. And so here's kind of a more clear illustration of that last problem I just described, is this runoff is going into these to-be-developed areas that are owned by the city. And so with that, I think I'll hand it back over to Jeff.
Thanks, Kyle. So the other initiative we have going on are looking at soil amendments that farmers might be able to use if we can't convince them to just stop working with this stuff altogether. And so the one is composted yard waste, fishbone meal, triple superphosphate fertilizer, and phosphoric acid. It's pretty well known that if you add excess phosphorus to soil when there's lead present, that under the right conditions, those will form a very insoluble mineral, which will make it less bioavailable. Organic matter will also bind it up. The fishbone meal is a little different. Fishbone is naturally high in phosphorus, and it's also organic. So the organic farmers in this region have an interest in this. This also has great applicability to urban agriculture, because a lot of urban soil is contaminated with lead because of the lead paint on houses. And a lot of them are organic farmers, and so they want to use something that's natural to treat their soil. This research is ongoing. Some of this has been done elsewhere, but this is we're demonstrating it in this region and then expanding that fishbone data. The other initiative is the pollinator islands that we're looking at. So ideally, we would just not have people use this land at all prior to really getting a more official cleanup done. But if we're trying to find some low engineering or non-engineered solutions. So one idea is put this land into conservation easements and then set up some pollinator islands, maybe get some ecosystem benefits back out of these lands. Of course, first question is, well, aren't you going to just poison the pollinators? And we're not quite sure. Lead is not preferentially absorbed into plant tissues, but it can happen. So we're investigating how well those plants can be propagated in this kind of soil, and then what kind of uptake is occurring. Then when we're looking for funding to do additional work in this area, once you've kind of got the research done and that's far enough along, we can apply for funding to do assessments or cleanups. A really good source for this is the EPA Brownfields program. They have a wide variety of grants that they give out. The biggest one is the grant program, the assessment program. This is where most of their money goes. They like to fund the assessments because what they're finding is a little bit of federal money that goes in and helps people identify what the problem is and the extent of the problem. That really jumpstarts local development. There are a couple different flavors of assessment grants. There's a community-wide grant, which is good for a town or small region that may have several sites that they want to look at. There's site-specific for one particular location. And then there's a coalition grant, which is for up to $600,000, and this is good for a group of cities or towns, a county, or even a coalition of counties. The people we worked with, we actually did apply for a coalition grant. Unfortunately, unsuccessful. We knew we were a little early in the process, but wanted to try to get everybody on board and thinking about this, and that kind of helped to catalyze that. It looks like we'll probably be able to go back in this year with some more focused grants in this area. One thing to remember is rural communities are not excluded. It requires a fair distribution between urban and non-urban areas and encourages cities or towns with populations of less than 10,000 to apply. Also, regions with persistent poverty and mine-scarred land get some extra bonus points. Now, you still have to have a solid proposal, which means you have to have an economic or jobs creation component to it, which can be a little challenging with rural agricultural lands. But don't rule this program out, because it is applicable to rural communities. So for economics, that we're looking at is, considering maybe rural solar. If you look at these pictures, that ground is covered. We're not going to have runoff, and with the solar panels there, nobody's driving their tractor through it, and you're getting a little bit of economic benefit. So we're exploring that with some of the communities we're working with as well. Just to summarize, there are mine-scarred lands in a lot of states. This is sulfide mining, which happens in a lot of places, and it has happened for the past couple hundred years. Local communities know of their mining history, but most have forgotten, or many have forgotten, the hazards that it still causes. The ag industry and agencies may not be aware of these hazards. NRCS actually provided money for some farmers in our region to spread out their low productivity soils to try to dilute it. And basically what they did is they created a much, much larger environmental contamination issue because they just simply weren't aware that the lead was there. Look towards institutional controls and low engineering interventions. Those can protect public health and can be done relatively inexpensively and quickly. And to keep in mind, the Brownfields program is a source for potential funding. And with that, we've presented what we were planning to present today. We'd like to thank North Central Regional Senator for Rural Development for the planning grant. And we've got some other funding sources from UW. And our contact information is below. We'll be happy to entertain any questions.
Thanks, Jeff and Kyle. One question I have is just sort of thinking about the potential impacts on kids, and so to what degree does this end up in the drinking water of, say, a well or something like that, and how might that compare with the Flint water crisis? Can you offer any insight in that kind of comparison?
Fortunately, lead tends to stay where it's put on the ground. It is not highly mobile. It could end up in the water table, especially when people are hauling stuff off site and throwing it in old rock quarries. That would be one avenue. The bigger hazard actually is exposure to the soil. Farmers getting it all over their tractor tires, driving it back to their farms. They have it on their boots. They bring it inside. Also, when it's dry out and they're farming and the wind is blowing, you can see the dust blowing. And these sites are often right next to houses. So where is that lead-contaminated soil blowing? So fortunately, it's not like Flint in that it's coming through the water pipes, but it is mobile in the environment. It's just because these are so close to homes that's really where the concern is. If it was way, way out in the woods, it would still be an issue, but perhaps not as immediate an issue as many of these are, because these towns exist because there were mines there. They grew up around them. So they're surrounded by this material.
Well, so maybe it would be more like in the years before we went to unleaded gasoline, and you have this gasoline exhaust with lead in it, and that having an impact. So when the wind is blowing, it just gets into your lungs and into your body.
Yeah.
So that's the impact.
Yeah. And again, farmers bringing it home. Another thing to think about is if the farmer's growing for silage, so that corn isn't getting very big, but they'll still run the harvester through it. And we do have some data from a researcher in Platteville that shows that there's a fair amount of lead in that corn. Enough that the phytoremediation people would call them hyperaccumulators, even though corn is not a hyperaccumulator of lead. But if you think, well, if you've got worst case, you got a farmer who has a small herd of cattle, he's farming a specific area that always ends up in silage for his cattle, well, those cattle are getting dosed. Industrial scale, it's going to be diluted enough, but if it's really just being harvested on a small scale, that could also be problematic.
Yeah. Okay, thanks. I don't see any other additional questions coming in through the chat. We'll wait for just another minute. I appreciate your work because we typically think these kinds of problems as having being in urban areas more, and so highlighting the rural implications is important. So thank you.
Yep.
Thanks for your work.
Yep. It was pointed out that I found the unfortunate connection between urban Milwaukee and rural southwestern Wisconsin.
Yeah. Well, maybe now is a good place to stop for today. Thank you very much for sharing your work, and I hope everyone has a good afternoon.
All right. Thank you.
Thank you.